This lesson is a continuation of equations and graphs of conic sections. This time we will talk about hyperbola, and then we'll look at generalized square root function. What's a hyperbola? Similarly as for the circle or an ellipse, we're looking for a locus of points with certain property. What kind of property? Well, hyperbola is a set of all points in the plane with the constant absolute value of the difference between the two distances from the two fixed focal points. So remember, in an ellipse we've been talking about the sum of the distances. So remember, in the case of an ellipse, if we had two focus points, then all points that belong to an ellipse have the following property. The distance of such a point from the first focal point and from the second altogether is constant. So if this is d1 and that's d2, then d1 plus d2 are always constant. However, in hyperbola situation, we are still looking at this d1 and d2, but we are making a difference between them. And since we don't know which one is larger, we just take absolute value of it. And this absolute value of distances is constant. So in the first situation we have an ellipse, in the second situation we have hyperbola. Okay, let's see the equation of hyperbola. Any hyperbola with the center at hk and the radius along the x-axis being a and the radius along the y-axis being b is given by this formula. So as you see, it's very similar to an ellipse. We still have x minus h, y minus k, both of them squared. We still have dividing by a square, where a is the radius along the x-axis, and b square, where b is the radius along the y-axis. However, in the case of an ellipse, we have a plus between these two expressions. For hyperbola, we have a minus. So that's one big difference in the formula. Also, on the other side, we may have either 1 or negative 1. There are two possible cases for a hyperbola, and we'll see in a second how this plus or minus affects the graph. So here we have the two possible hyperbolas. Both of them are with center at 0, 0. And the first one has equation x squared over a squared minus y squared over b squared equals 1. Positive 1. The graph of such hyperbola turned out to be shaped along the two asymptotes. Those asymptotes, first of all, they intersect at the center of hyperbola. Secondly, those are lines with slope of b over a, either positive or negative. One asymptote is rising, so it has a positive slope, and the other is declining, so it has a negative slope. The slope of asymptotes is plus or minus b over a. We're using the same letters a and b that describe the radius along the x or radius along the y-axis, meaning that the a can be identified with this segment. So this point, the vertex of our hyperbola, is at a, and then if we move it up towards the asymptote, the height, this point will represent the distance b. Okay, this is really good because it will help us in the future to graph any hyperbola. As long as we have a and b, what we can do, we can start from the center, go a steps to the right and a steps to the left, that's negative a here, and then go b steps up and b steps down. Draw a rectangle with sides 2a and 2b, and then if we connect the opposite vertices of this rectangle, we'll draw asymptotes. As soon as we have asymptotes and we also have the vertices of our future hyperbola, we'll just volunteer a shape that will try to approach, but it will try to follow the asymptote starting from the vertex. The only thing that we need to determine is If the hyperbola is positioned as on this diagram, that means horizontally, or maybe it is positioned vertically like this. The horizontal or vertical position depends on positive or negative 1 on the right hand side. However, notice that the left hand side of this equation should start with x, and then y, and then plus or minus 1. So on this diagram, the equation is given with y first and then x. If we want to rewrite this with x part in front, we could, for example, multiply the whole equation by -1, and that's equivalent to x squared over a squared minus y squared over b squared, and then it's equal to -1. So you see, if we start with x, then with y, and the right hand side of the equation is +1, then we have a graph positioned horizontally, and if it's -1, the graph is positioned vertically. Let's notice that this equation of an asymptote is so simple for these two examples, just because the asymptotes are coming through the origin, so we don't have to accommodate for the y-intercept. But general equation for an asymptote for any hyperbola, it will start with plus minus b over a, the slope, times x, but then we'll have to add some constant here to accommodate for the y-intercept if the asymptote needs to be moved to different place. So that's in case when the center is not at 0, 0, but at hk. You can always plug in those given h and k coordinates to the equation and figure out what the constant is. Okay, so let's graph some hyperbolas. In this example, we're asked to find the center, radii, and equations of asymptotes of each hyperbola, which will greatly help us to graph. Okay, so what's the center? Coordinates of the center, as you remember, are those numbers that we subtract from x and y. But here we don't subtract anything, so the coordinates of the center are 0, 0. Now the radius along the x-axis is square root of 4, so it's 2. The radius along the y-axis is square root of 9, so it's 3. And equations of asymptotes are y equals plus or minus b over a. So b is 3, a is 2, plus minus 3/2 of x. Okay, so let's gently graph those asymptotes. The line y equals 3/2 x passes through the origin and has a slope 3/2, which means we can go 2 steps across, 3 steps up. So this point, that point, and similarly to this point needs to be connected. Let's try to connect it by a dashed line. Similarly, the negative one is 2 across, 3 up, so it's this point, and that point. Let's connect them by a dashed line. Okay, now let's plot the radii. Rx is 2, so 2 steps across on the x-axis both ways from the center, and ry is 3, so 3 steps up and down. Now let's draw the rectangle that passes through those points. And finally, let's draw the shape of hyperbola. Since we have the order x, y, and here's 1, the hyperbola will be positioned horizontally, so the vertices will fall into number 2 and -2 on the x-axis. And then the shape will try to follow the asymptote direction. So let's graph it. It will go somehow like this. And similarly the other branch, closer and closer towards asymptotes, like this. Here's our hyperbola. Another example. Again, let's list the center. The coordinates of the center are hidden here. So opposite sign to whatever you see in the bracket, meaning 1 and -2. Rx is the square root of 9, so it's 3. Ry is the square root of 4, which is 2. And equations of asymptotes are y equals b over a plus minus 2/3 x. Except that this time, since the asymptotes intercept at the center, but the center is not 0, 0, we'll need to add some constant here. We could calculate this constant exactly, but there is an easier method. We don't really need to worry about this constant at this time. Let's see how this can be done. Let's start with the center. The center is at 1, negative 2. And we'll build the whole diagram around this center. This point will work like the origin in the previous example. So now we need to mark the radius along the x. That means stretch from the center 3 steps to the right and 3 steps to the left, and mark those points. Similarly, radius along the y. Let's mark 2 steps up and 2 steps down from the center. Okay, now we're ready to graph the rectangle. This rectangle tells us the position of asymptotes. The asymptotes are the lines that join the opposite vertices of this rectangle. So let's graph the asymptotes. One and the other one. Okay, as soon as we have asymptotes, we're ready to graph our final shape of hyperbola. The last thing to check is this hyperbola positioned horizontally, the same as the previous one, or vertically? Well, since this is x, y, and here is 1, it will be positioned horizontally, meaning the vertices are these 2 points, and we'll try to shape our curve closer and closer towards the asymptotes, so it will look somehow like this. Similarly on the other side. And let's see the last example. Oh, this time we don't have the order x, y, and 1, so maybe it's better to rearrange it. To start with x term and then y term and then the constant. To rearrange it and to start with a positive x term, it's a good idea to multiply by a negative 1 here. Okay, so we'll have x squared over 9 minus y squared over 16 equals, oh, that will be negative 1. So this time, let's remember our shape will be positioned vertically, like this. Okay, let's start with listing the center. The center this time is really easy. It's 0, 0. The same as in the first example. The radius along the x is 3. The radius along the y is 4. And the hyperbola will be positioned vertically. One more thing, equations of asymptote is y, and this time we don't have to worry about the constant, is just plus minus 4/3 x. But again, this equation is kind of extra. We don't really need to know it in order to graph the hyperbola. So we start with 0, 0. We open our wings by 3 steps to the right and 3 steps to the left. And then 4 steps up and 4 steps down. Now we can gently draw the rectangle, pretty big this time, and mark asymptotes as diagonals of this rectangle. Okay, now we're ready to graph our hyperbola. Since it's positioned vertically, the 2 vertices will be on the y-axis, and we'll try to volunteer a shape of our hyperbola, thinking about how the asymptotes are going and follow those roads. So here's our final hyperbola. Okay, let's review the process. How do we graph hyperbola? First of all, set the equation in order something with x minus something with y equals to either plus or minus 1. If it's plus 1, the hyperbola will be positioned horizontally. If it's minus 1, it will be positioned vertically. Then plot the center, draw the box using the radii along the x and y axis, draw the diagonals, those will be your asymptotes, and finally volunteer the shape of hyperbola, starting with the vertices that are midpoints on appropriate sides of the box and going closer and closer towards the asymptotes. Every hyperbola has 2 branches. In the end, let's talk a bit about a generalized square root function. What does this mean? Let's say we have a function g of x and we know how to graph it. How would we graph square root of it? Okay, let's see some examples. In the first example, we want to graph the function root of 9 minus x squared. Well, what's under the root? Under the root we have 9 minus x squared, which is a parabola. However, before we start graphing anything, we should think about domain and possibly range. Domain for sure. Range, sometimes it's harder, but we'll try to figure it out. Sometimes when we start graphing our function, plotting points, it gives us better idea what the range is. So let's see. To find out domain, we need to protect the radicand. The radicand, that means everything what's under radical sign, must be positive or 0, bigger equals 0. And then to solve it, we can move the x to the other side, x squared smaller equal 9, and then we can apply square root on both sides. But now we need to remember that root of x squared is not really x. That's not true. It's absolute value of x, because x by itself could be negative, but on the other hand, square root will give us always positive answer. So we have to make sure that our result is always positive. That's why we need to put absolute value here. So absolute value of x is smaller equal root of 9, which is 3. And then how do we solve this inequality? Well, let's recall what absolute value stands for. It gives us a distance from 0. So we're looking for such a number that is not more than 3 steps from 0. Okay, if we imagine a number line here and a 0, we can go up to 3 steps to the right with the endpoint or to the left. So our domain is from -3 to 3. So x can oscillate between -3 and 3. Therefore, this is the solution. And we can write the domain of function f as interval from -3 to 3. That tells us that the graph will be positioned from here to there and only there, no farther than this segment. Okay, but we still don't know how the shape may look like. Here's my suggestion. If we rewrite this equation by using y, let's rewrite it on the right hand side here, and then it's root of 9 minus x squared. We could rearrange this equation, for example, by squaring both sides. Okay, so we would have y squared equals, when I square the root, I end up with whatever is under the root. Since our x's are in domain, the radicand is already positive, so there is no need for absolute value. Now notice that if I move the x squared to the other side, I end up with well-known equation. What is it? Well, it looks like a circle with center 0, 0 and radius 3. Okay, so the circle with center 0, 0 and radius 3 will look like this. However, this graph is for this equation. It's not necessarily the graph of that equation. How come? Notice that the original equation has y, f of x, which is y, always positive or 0, because square root of something will never be negative. So, since y is always bigger equals 0, then we can keep only the top part of the circle with the endpoints on the x-axis. All those points on the bottom half of the circle do not satisfy the original equation. They do satisfy the modified equation here that helped us to figure out what is the shape. However, we are still obligated to graph the original equation, which means the bottom points needs to be erased. They do not belong to the graph. And now the combination of investigating our formula and seeing the graph gives us enough information to state the range. So the range is a segment from 0 till 3, inclusive with the endpoints. Okay, so we have a square root of parabola that gives us half a circle. Let's see one more example. Again, we can start with investigating the domain. That means our radicand must be positive or 0. So let's calculate. 1 minus x squared over 4 must be bigger equals 0. That means that x squared over 4 is smaller equal 1. Or finally, x squared is smaller equal 4. Now when we take square root on both sides, we end up with absolute value of x is smaller equal 2, which similarly as before tells us that x oscillates between -2 and 2. So the domain of f is the interval from -2 to 2. Okay, so we know that our graph will have to fit within this region from -2 to 2. However, how this graph looks like? Maybe as in the previous example, try to rearrange this equation to recognize the shape. Again, replace f of x by y, which is -3 and root of 1 minus x squared over 4. Now we could divide by -3, so it's y over -3 equals square root. And then if we square both sides, we end up with y squared over 9 equals 1 minus x squared over 4. Oh, that looks already familiar. As soon as I move the term with x to the left, x squared over 4 plus y squared over 9 equals 1. You could probably recognize the shape already. What is it? Yes, that's an ellipse. Okay, let's graph this ellipse gently, and then we'll think of which part of the ellipse should be taken. How do we graph it? Center 0, 0, radius 2 along the x-axis, radius 3 along the y-axis, and the ellipse goes somehow like this. Okay, now let's go back to our original equation. And now what do we know about y? The y is always negative or 0, never positive, because it's negative root. Okay, therefore since y is always smaller equals 0, and we know that it's part of this ellipse, that means it's a bottom part of it. So the graph will look just like that with the endpoints. We could erase the top part, and now it's easy to answer the question about the range. The range is the interval from -3 to 0. That's the range. Okay, so that's how you can deal with root of certain functions. Obviously not every function, but quite often if you rearrange the equation so you can get rid of the root, it's possible that you will end up with something familiar like a circle, an ellipse, or hyperbola, and then you decide which half of this conic should you actually graph.